Welcome to this video. Previously, we studied motion along one straight line. In this part, we extend those same ideas to motion in a plane, where objects can move both horizontally and vertically. Most real motions are not perfectly straight. A ball follows a curved path. A car may turn, and a boat may move across a river while the current pushes it sideways. When motion takes place in a flat plane, we use two-dimensional kinematics. The important point is that this is not a completely new topic. It is an extension of one-dimensional kinematics. We will describe motion in the x direction and the y direction separately. To separate motion into x and y parts, we must be comfortable with right triangles. Before we can work with motion in two dimensions, we need a quick trigonometry review. This slide shows the basic right triangle we will use many times. The longest side is the hypotenuse labeled h. The side next to the angle theta is the adjacent side labeled HA. The side across from the angle is the opposite side labeled HO. When we break a vector into components, these sides will represent the horizontal and vertical parts of the vector. Once we know the sides, we can define sine, cosine, and tangent. For a right triangle, sine, cosine, and tangent compare different sides of the triangle. Sine of the angle is opposite over hypotenuse, and we can indicate as sine theta equals length of opposite divided by length of hypotenuse. And cosine is given by the adjacent divided by hypotenuse. So here cosine theta will be equals to length of the adjacent divided by the length of the hypotenuse. And tan is given by the opposite divided by adjacent. So tan theta is equals to length of the opposite divided by the length of the adjacent. There is a word that you can remember to keep this relationship in your memory. SOH CAHTOA, SOHCAHTOA. So if you remember this word, this tells you sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tan equals opposite over adjacent. In physics, we use sine and cosine most often to find components, and we use tan to indicate direction angle. The other key relationship for right triangles is the Pythagorean theorem. The Pythagorean theorem says that the square of the hypotenuse is equals to the sum of the squares of the other two sides. So the square of the hypotenuse is equals to square of the opposite plus the square of the adjacent. This is how we find the magnitude of a vector when we know its perpendicular components. Now let us use this relationship in a quick example. In this example, the adjacent side is 3.5 meters and the opposite side is 2.5 meters. We are asked to find the hypotenuse and the angle theta. This is exactly the type of calculation we will do later for vectors. First, we find the hypotenuse and then the angle. First, let's write down the known values. HA is 3.5 meters, HO is 2.5 meters. And then we are going to use Pythagorean theorem to find the hypotenuse. So h square is equals to HO square plus HA square, and then h will be equals to square root HO square plus HA square, and then we will substitute for this. This is equals to 2.5 meters square plus 3.5 meter square root, and then this is equal to square root of 18.5 square meter, and that is equals to 4.30 meters. And to find the angle, we use theta equals tan inverse HO divided by HA. So here we have tan inverse 2.5 meters divided by 3.5 meters, and this is equals to tan inverse 0.714, and this is equals to 35.5 degrees.